What's up, everyone? It's your boy Jaden, and I'm here to explain moment of inertia because it's a concept that's pretty confusing for a lot of people, and it's also confusing for me. So, let's get to the basics of rotational inertia. I'll also walk through two mastery check problems and try to help y'all with the approach there, but yeah, let's get into it. So, where did moment of inertia come from? We actually derived it from the kinetic energy of a system, which is equal to the sum of the kinetic energies, and that's equal to the sum of 1/2 mv squared. Dude. Okay, so pretty much what we did after that was we said, okay, if there are multiple point masses, let's just look at one of them. So one point mass would be 1/2 m1 v1 squared. Okay, and we can replace velocity with r omega when if it's rotating. But the reason we can replace it with this is because of the definition of a radian. So a radian is basically the arc length divided by the radius. That's the definition of a radian. Okay, and pretty much what we did was we multiplied the radius over and said the arc length is equal to the angle in radians times the radius. And we took the derivative with respects to time of the whole thing. And since the arc length, the speed of it might change, we changed that to the velocity, the tangential velocity. So if we were to look at it like this, the speed at which the object rotates around the arc length, vt, is equal to the speed of how, like, the speed of the arc length changing is equal to uh, the the radius, which is going to be constant for that one point mass, times um, d theta over dt, which is basically equal to r omega. Okay, now that we got this, we can plug this back into our original formula. So 1/2 m r omega squared. And now, since this is multiplied, we can square both, and it'd be the same thing. And then we got the definition of the moment of inertia, which is this thing. This is the moment of inertia for a particle, also known as the rotational inertia. And we represent this with the letter I. I. Okay, so for any point mass, the definition of the moment of inertia is mr squared. But however, point masses don't show up that much in the world because we usually have multiple things. So the I of a system is equal to the sum of all the individual I's. And I don't write it on the sigma, but the sigma notation for this would be from any number of individual particles to n. So there could be I plus, well, this wouldn't be equals to, it would be equal to I1 plus I2 plus dot 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 I to the nth. Okay, now let's get down to big stuff, which is the sum of the MIRI squared. Okay, give me a moment. Parents are calling me for lunch. I'll be back in a second. Hopefully y'all didn't spend too much time. Okay, let's get back to it. Um, so pretty much this is what we can use. But in our mastery check, a lot of the objects that show up are distributed masses. And pretty much a distributed mass has an infinite number of particles. So what we can do is change the I of a distributed mass is equal to the integral of mi, no, frick, r squared dm. And where does this come from? Well, the m1 r1 squared for a ton of particles. Let's say we look at one very tiny particle and we're going to add up all the tiny particles. So the m turns to dm. And since we're adding up an infinite number, we change the sigma sign to an integral sign. I think that's a sigma sign. And then the Ri for each individual particle just becomes R because each little tiny mass has some R from the point we're looking at. And we keep this squared. So, since it's standard notation, we put dm at the end. So this is our integral formula. And we can use this to conceptualize a lot of things. So using one dimension, two dimension, and three dimension, we can pretty much derive a lot of the, what's it called? We could derive a lot of the moment of inertia for different distributed masses using these basic thingy-majiggies. Okay, so now let's actually try to answer a problem. Okay, so for this question, it says there are 2 point masses, 1.1 kilogram and 1.26 kilograms, attached to either end of a uniform rod that has mass 4.4 kilograms and a length of 2.3 meters. So what does that look like? Looks like this. Just imagine that these are point masses, even though I'm drawing them to be quite big. So this is 1.1 kilograms, 1.6 kilograms, and this right here is a rod, length L and mass M, which we can also replace these with M1 and M2. Okay, so now that we got these down, we got the image, we just need to find the rotational inertia about the system, about an axis that is perpendicular to the rod. So if this is the rod, it's going to be perpendicular to it. And so it can rotate in either this direction, or if it's coming towards you or towards the page, it can rotate in this or this direction. Um, and we're looking for the center of mass of the system. So it's not just going to be smack in the middle. The center of mass is going to be displaced because this mass is heavier, so it's probably going to lean a little bit towards this side. So let's get back to the center of mass formula. So the way I approached this was mx center of mass is equal to the sum, or m1 x1 plus m2 x2 plus m3 x3. And the reason I chose m3 x3, even though this is a distributed mass, is because of symmetry. We know that the center of mass for this rod is going to lie at L over 2, so we can use that. Okay, and now we gotta establish a coordinate plane. So how about we say that right here, oh frick. Uh, okay, let's just say that this is the coordinate plane x and y. Y is not really important, so let's just look at x. So the center of mass is just gonna be m1 x1, which is at 0. So boop. m2 x2, let's just say that's the rod. Um, that's just gonna be L over 2, well, M times L over 2. And then for this one, it's just gonna be L M3 times M2 times L. So the x center of mass is gonna be equal to ml over 2 plus m2l divided by the total mass of the system. So this would be m1 plus m2 plus l. I mean m. Okay, now that we know the x center of mass respect to this axis, we can plot that point. So it's just going to be, let's say this is the x center of mass. We're trying to find the rotational inertia about that axis. So I'm going to redraw the diagram right down here. And let's say around here is the x center of mass. And this is where we're trying to find the I center of mass for the system. Okay, so what is a rotational inertia again? Let's go back to the basics. R squared times dm. So each individual little dm, we're trying to find its R squared value, and that's going to be equal to I of the system. So from this point, we have a lot of little dm's. We got a dm over here and a dm over here. And pretty much each of them have a different R squared value. So what we can do is we can use the parallel axis theorem, find the the rotational inertia about this one point that we established. And the parallel axis theorem states, I can't spell parallel, is that the I about a point of your choosing is equal, or like the axis parallel to any of that, equal to the I center of mass plus the mass of that object times the distance from the point you're choosing squared. Okay, so for this question, um, we're gonna have to use this formula one time, and that is because the I center of mass of the rod is different from the axis of the where we're choosing, the axis that is coming straight towards you from the page. So that would look like I of this system is equal to the rotational inertia, the sum of all the i's, which is going to be equal to the I center of mass of the rod, which is going to be 1/12 ml squared. You should have derived this in class, plus m times. And now we have to find the distance from the x center of mass. So let's say this is L over 2. This is the x center of mass. So the difference between that would be x center of mass minus L over 2. And you should get a very small number for that because it's quite close to the center mass squared. And then you would add this to the little point masses, which we can use m1 r squared plus m2 r squared. So this is all we need to find the moment of inertia for the system. Okay, let's do the second question. This one's very similar to the first one, but this time we got two spherical masses. So we got a sphere here, got a sphere here, and we got a rod that connects them. We're asked to find it through the center of this one. So let's just run through very quickly because I have to eat lunch. This 1.2 kg, this one's 0.5 kg. About this point is going to be equal to the rotational inertia of that one sphere plus this rod, this center of mass, we gotta use parallel axis theorem to find it about this axis. So it'd be 1/12 m, and the distance ml squared plus let's call this r1, and this whole thing L, so it'd be r1 plus L over 2 squared. And then we would add that with the third sphere, which would be, we'll have to do the center of mass here and then do the parallel axis theorem again. So that'd be plus 2/5 m r squared plus m, that's the mass of that second sphere, times r1 plus L plus r2. Let's say this is r2 squared. And this formula will get you the moment of inertia about this one point. So yeah, that's it. If you have any questions, just put them in the comment section. I'll try to answer them. See ya.